Here we go. Welcome to week 7 of distance learning. You may or may not be glad to know we're done with matrices. Congratulations. There were some things we cut out of the matrix unit that we would have done had we been in class. We really kept it to the basics, and so just keep that in mind. If you're going off to college next year and you see matrices, there was some that we did not do, but you do have a good foundation to be successful in any class where you do matrices in the future. So this week we are switching to a probability unit, and it's not all just straight probability, like what are the chances of getting heads if you flip a coin 5 times. There'll be some other things involved. What we're talking about today is combinations, so it's really probability and combinations. If you look at the second page of the notes for today on the back, you'll see the very first problem. A man's getting dressed. He has 5 shirts, 7 ties, 4 pants, and 3 shoes. How many different possible combinations can he make with that? And that's what we're focusing on today. And we're going to be talking about something called the fundamental counting principle, which is an awesome, useful tool. But even before we get into that, we have some vocabulary to talk about, which you'll see right here on your notes. And even before we talk about the vocabulary, I want to come up here at the beginning of your notes and talk about what an n factorial is. This is like a basic, sort of like a pre-skill for this unit. We won't be working with it a lot today, besides just introducing it. We'll be doing it more in the next lesson. So this word factorial means you take a number, like 5, for example, right here. Now you see how it has 5 and exclamation mark? That does not mean, like, yay, 5! It means 5 factorial. When you get to the exclamation mark, you say the word factorial. And what that means is this: you take the 5 and you take all the integers that are below 5. There's 4, 3, 2, and 1, and you multiply them together. And that's 20 times 3 is 60, times 2 is 120, times 1, and you get 120. That's what 5 factorial is. In general terms, so I'm going back up here to the definition. For any whole number n, the factorial of a number is the product, which means multiply, which we did in that specific example. The product of the natural numbers, I think I said integers, which includes 0. You don't include 0. The natural numbers less than or equal to that number. By definition, 0 factorial is 1. So it will always be 1 anytime you see a 0 factorial. And so n factorial in its general form is the number n times 1 less than that, times another 1 less than, which would mean 2 less than where you started, times n minus 3, times so forth and so on until you get all the way down to, which is what we did here. We had 5 times 5 minus 1, which is 4, times 5 minus 2, which is 3, times 5 minus 3, which is 2, and then times 1. So I want you to take a minute and pause the video and try numbers 2, 3, and 4 on your own. You'll notice that 3 and 4, you're starting with pretty big numbers. So to handle those, you probably don't want to multiply them in your head or by hand. Use the Desmos Scientific Calculator at this website under the Func tab, F-U-N-C for function, or you can use your cell phone. Turn it sideways to display the additional functions that your phone calculator has. So take a minute using those methods and go calculate 6 factorial, 10 factorial, and 18 factorial. For 6 factorial, I'm not going to go to the calculator. I'm going to show it to you. Since it's pretty short, I'm going to, just for repetition's sake, explain one more time what it means. It doesn't mean 6, yay! It means 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, which is just the previous thing we had, 120 times an additional 6. So that's 720. And then if you went to Desmos or your calculator and did these factorials, you should have had this. 10 factorial is 3,628,000. And 18 factorial is whatever kind of craziness this number is. All right, so that's basically nonsense, but there you go. You got practice with your calculator. All right, so that's the concept of factorial. One thing I want you to notice here is that we're multiplying numbers by each other, which is something we'll be doing with the rest of the lesson. This was just a particular kind of format where it was 5 times 4 times, 1 less than what you started with. So a little bit of vocabulary that we'll be talking about today. An experiment is any task that can be done repeatedly and has a well-defined set of possible outcomes. So let's say you wanted to know the odds that you would get heads whenever you flip a coin. Well, you could repeat that experiment over and over and over. And the well-defined possible outcomes is you could either get heads or tails. Like there's no confusion about what the outcome might be. A trial is each repetition of your experiment. So if I flip that coin 10 times, I had 10 trials. A sample outcome is any potential outcome. Of a trial. So with going back to the coin, my sample outcomes are heads and tails. And a sample space is the set of all the possible outcomes. So not talking about them individually, but talking about how many there are altogether. So flipping a coin, my sample space, there's 2 possible outcomes. It's heads or tails, and that's one. The set of both includes both of them. This could probably be extended to use our vocabulary as just sample outcomes. The sample space is the set of all sample outcomes, which we defined. So a tree diagram is a graphic of all the different outcomes that you could have based on your trials. So it's more than just saying, oh, I flipped a coin, I got heads or tails. It's saying I flipped a coin 5 times. What were all the different orders that I could get from that experiment? Like, did I get heads, 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 heads 5 times? Did it go heads, tails, heads, heads, and then tails? This is a picture representing all the possible outcomes you could have had. It's your picture of your sample space. So it's an organized display of combinations of events using branches. And so here we go with this example. For a fair coin, meaning it's not like, a weighted coin and someone's trying to rip you off and take all your money on the side of the street somewhere. It's a fair coin. we are going to draw a tree diagram illustrating all the possible outcomes for 4 flips. And then B, we're going to create an ordered list of all those possible outcomes. So here's A, drawing the actual tree diagram. The very first flip, so you flip the coin. What are your options for that first flip? You can get either heads or tails. And on the second flip, yes, you can only get heads or tails, but we're sort of going to show the progression of the possible ones, assuming you got heads on the first flip. You can get either heads or tails next. And assuming you had tails on the first flip, if that was your starting point, after that, you can either get heads or tails. Same thing with the third flip. So for example, what's starting to happen here is if I had heads on the first flip and heads on the second flip, I could also have had tails on the third flip. You're starting to see a progression of all the flips, all the different ways, all the different outcomes you can get. If I was heads first and then tails on the second, I could get heads, tails again there. And then if it was that I had, so that was all the possible outcomes I could have so far if I had heads on the first flip. Let's say I had tails on the first flip, so now I'm here. And then the fourth flip. It's getting ugly. So what I want you to understand here is how many outcomes I just showed. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes. And you can thread your way back up and find all the different ones. Like if I wanted to, I could say, well, let's say I had tails on the first flip, and then heads on the second, tails on the third, and then tails on the fourth. That's one of those 16 paths, one of the 16 options that you could get flipping a coin. And so now we're going to, so this is just a tree diagram of all the options, and we're going to use that to write out all the options. So there's 16 possible outcomes. For example, if I had heads the first time every single time, I would write that as this. Heads on the first flip, heads on the second, the third, and the fourth. That is this progression right here. But I could have gone heads, 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 and then to tails on the last one. And if I were to write that out, it would look like this. Heads, 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 and then tails. And you can do that for every single of the 16 possible outcomes. You could do that. I don't know that we really want to do that, but I would like to give you, excuse me, a shortcut. And this is going to lead us into the fundamental counting principle. So here's your shortcut. There were 2 possible outcomes, 2 potential outcomes for the first flip. You could get heads or tails, 2 things. This one or this one. But how many outcomes were possible for each of those? 2 possible outcomes for the first, 2 possible outcomes for the second. Well, how many outcomes is right there? That's 4, right? So 2 for the first, 2 for the second. How many possible outcomes were there for the third flip? Still 2. What's 2 times 2 times 2? It's 8, right? Count how many outcomes were right here after the third flip. 1, 2, 3, 4, 5, 6, 7, 8. And so you probably see where this is going. For the fourth outcome, there was another 2 for each of those 8. And 8 times 2 is 16. Okay. All right, so the fundamental counting principle says this. Given any, oh my gosh, I cannot talk. Miss Farias talks, take 2. Given any experiment with 3 defined tasks, if there are P possibilities for the first task, Q possibilities for the second task, and R possibilities for the third, the total number of ways the experiment can be completed is P times Q times R. So here's how that corresponds to the example we just did. In the example we just did, there were 4 defined tasks. There was flip 1, flip 2, flip 3, and flip 4. And there were, so that was a 4 here for the 3. There were 2 possibilities for the first task or first flip. There were 2 possibilities for the second task or flip. 2 for the third, and then 2 for the fourth. So while this says 3, it's just a specific general example. And then how did we find the total number of outcomes using multiplication? We just multiplied them. And we got 16. Okay, and that's all this is saying right here. And so we're going to do some examples of this. So read example 1 to yourself, pause your video. It says a frugal businessman has 5 shirts, 7 ties, 4 pairs of dress pants, and 3 pairs of dress shoes. Assuming that all possible arrangements are appealing, how many different shirt, tie, pants, shoes, outfits are possible? And the reason why we have to say that they're all appealing, so that you don't get bogged down with questions like, well, he really doesn't like his green shoes, so he's going to choose the other ones more often. So remember, it has to be all possibly fair outcomes with, and so we have to say something like that, even if it sounds silly. So what are the defined tasks? So that's what the fundamental counting principle says right here. There are defined tasks. In this problem, the defined tasks are, he has to pick a shirt, a tie, a pair of pants, and we really do hope he picks a pair of pants, don't we? And then shoes. I always like to set up my problems with these little bars to help me visually see the tasks that are having to be decided. And then I put a number above each of those lines that shows the number of possibilities for each task. So what are the possibilities, or how many options does he have to choose for shirts? Yes, 5. How many ties does he have to choose from? 7. How many pairs of pants? 4. And how many pairs of shoes? And to figure out the total number of possible outcomes, we multiply those things together. And we get 420. So he's got 420 different outfits possible. It literally is more than a year of outfits that he has without repeating one. So you pause and try the next one. So report cards, grades at a local college consist of A, B, C, D, F, and W. W probably is, by the way, stands for withdraw. Pro tip, if you withdraw a class before the drop date, it will just show up as a withdraw and not a failure on your transcript. If 4 classes are taken, how many different report cards are possible, right? So first you have to figure out what your defined tasks are. The defined tasks are the grade in each of the classes. What grade did the college student get? So we need to figure out the first class, the second, third, and fourth. And how many report card grades are possible? Well, we just count them. There's 1, 2, 3, 4, 5, 6. And then 6 for the next one, and 6 for the next, and 6 for the next. And then we just multiply those together. 6 to the 4th power is 1,296 possible report cards. Okay. Pause your video and try the next one. If I was born in March, April, or May, after the 19th, but before the 30th, and after 1949, but before 1981, how many different month, day, year dates are possible for my birthday? Just in case you're hacking someone's computer. I don't know. Trying to figure out their password. I have no idea. Take a minute and I want you to just set up the problem and I want you to think really, really hard about this part of the problem. Okay, so here are the tasks. We want to know how many different months there are, how many different days there are, options, that's the DD, this is the MM, and how many different year options there are. That's the Y. All right, so how many months did you come up with? There's 3, right? And how many days did you come up with? It feels a lot like it should be 11 days, right? Because 30 minus 19 is 11. But let's actually take a minute to write down the possible dates. The highlighted green part says after the 19th. What's the first date that comes after the 19th? The 20th, right? Dang it, what is with my pen? And then the 21st, 22nd, 23rd, 24th, 25th, 26, 27, 28, 29. Does not include 30. It says, but before the 30th. So how many days is that? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So there's really only 10 possible days. In the pattern here, when you get to other problems like this, is it's 30 minus 19, which is 11, but then you just take off 1 to get to that same. So let's do the same thing for the years, but because we just discovered this pattern right here. So, oops, I did it again. I think I need more coffee. Subtract subtract the end dates, and then one more to get the actual number you need. Because look at this. That was okay to write out the dates between the 19th and the 30th, but do we really want to do that for figuring out the years? Like, do you want to write down all the dates between 1949 and 1981? I mean, you're welcome to, but I don't recommend it. So we're just going to do this same pattern that I highlighted in yellow, but we're going to do it for the years, right? So that would look like this. 1981 minus 1949 is 32. But then what did we do next? We subtracted 1. That accounts for the thing that says after this and before that. Okay, is that minus 1? And so there's 31 possible years. And what are we going to do with those numbers? 3, 10, and 31? Going to multiply them. So there are 930 possible dates for this person's birthday, in case you're trying to hack their account and think that their birth date is their password. You have 930 options that you can try. All right, last one. Replacement or no replacement. It says determine how many ways 3 numbers can be selected from the numbers 0 through 19 if replacement is allowed or replacement is not allowed. So replacement is allowed means the numbers can repeat. And then on B, replacement is not allowed means the numbers aren't repeating. So how many tasks are we deciding here? 3 tasks. We're deciding the first number, the second number, and the third number. Well, if replacement is allowed, that means repetition is okay. Repetition, okay. How many numbers are there to choose from for the first one? If you said 19, you'd be wrong. It's not just 19, it also includes 0. See, if you had 0 to 2, that's really how many numbers? 3. It's the 2 that you're going up to, but plus 1 more to include 0 as a digit. So if I'm choosing from the number 0 to 19, there's really 20 options for me. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah, blah, all the way up to 19, that's 19. And then plus 0 is 20 possible numbers. And since repetition is allowed, there's 20 options for the second number and 20 options for the third number. And then we multiply those together and we get 8,000. 8,000 ways. So how does this look different when replacement is not allowed, which means no repetition? Well, it looks like this. There's your first number, your second number, and your third. There are still 20 options for your first number, but once this one gets decided and you're not repeating anything, how many numbers do you have optional for the second number? You have 19. Because whatever went in the first spot can no longer be used. And now whatever went in the second spot can no longer be used. So how many numbers are remaining to be picked from for the third spot? 18. You can see how that's starting to look kind of like a factorial, which we talked about at the beginning of the lesson, right? So that's, and then we multiplied those together. 20 times 19 times 18, there are 6,840 ways that 3 numbers can be chosen from 0 to 19 when no repetition is allowed.